Hello everyone, Chris Miller here. Before you watch the video from my class today, I need to talk directly to those of you who are not in my class and watch my instructional videos on YouTube. For those of you who do not know, I'm a professor in the Department of Statistics at the University of Nebraska-Lincoln. Administrators at my university have recommended the elimination of my department. All faculty, including me, will lose their jobs. I will not be able to post an instructional content like this to my YouTube channel anymore. And also, most students in the department will not be able to complete their degree programs here. It may seem strange or odd to you that a university would actually eliminate a Department of Statistics given the growing importance of statistics, data, and data science in general for the world. And we all feel exactly the same here. There is still a chance, though, that administrators will change their recommendation. If you like the content that I make available on YouTube, and if you think that statistics is important, please let my administrators know it. In the content description for this video, I've included information about how to send them a letter or just a small comment. With your help, I hope we can save the Department of Statistics, and if we are successful, I promise to continue posting these instructional videos. Thank you very much. Let's begin class here. So today we will finish up principal component analysis. You'll have an opportunity to work on project number 1 with your group members corresponding to my post to the discussion board last night. And project number 1 is due Tuesday, October 14th at 5 p.m. So once again, save our stats. Have your voice heard if you haven't already. This website and make your voice known. Okay? Okay, so let's finish up these notes. We don't have much more. So we're going to talk about the serial data now with respect to principal component analysis. Before the last 2 times that I taught this course, actually the serial data was usually what I presented first for an example with PCA. I decided to move it later in the notes because I thought the goblet example is a better example, because that's a place where you would actually want to do it, where with the serial data, since we only have 3 variables, why would you even use PCA? But the key is, again, we often will use particular data sets to illustrate something because it's, from a teaching perspective, it's helpful. And so I decided, rather than totally throwing out this example, I put it at my end of my notes. I'm not going to go through in as much detail as I did with the goblet example, but I do strongly recommend that you read the detail as a way to make sure you understand what's going on here. So with the serial data, we have 3 variables of interest. And so when you come into a principal component analysis, you have to make a decision of, first of all, would this actually work? Would it be beneficial? And if you saw 3 variables, you'd say, no, you shouldn't do it. But let's ignore that. And so what you could do first is find an estimated correlation matrix. Take a look at those correlations between those variables. Do you think principal component analysis is going to be useful? It's definitely questionable. Because remember what principal component analysis does. It tries to take advantage of the relationships that you have between variables and then form new variables that are distinct, and hopefully the number of new variables that you need are less than what you started off with. If you already have distinct variables, uncorrelated variables, principal component analysis is not going to help you at all. And yes, there is some correlation there, but it's not much. Now, then you have a question of, should I use the correlation matrix or the covariance matrix? Typically, you should always use the correlation matrix. And in this particular case, though, notice we have 2 variables that are measured on a per grams basis. We also have one that's milligrams. So you might be thinking, okay, let's just transform that milligrams to grams. You could do that. The problem that you're going to see, though, and I will illustrate this later, is that the variability for sodium comparison to the other ones is going to be so much greater that that's going to throw off your entire analysis. Because remember how principal component analysis works. It tries to explain as much variability in the data as possible, where that first principal component is the highest amount of variability that's possible that's explained by a new variable. And if you have a variable in your original data set that just has so much more variability than the other, then what will happen is your first principal component essentially becomes that particular original variable. You'll see that coming up. So we're going to use the correlation matrix here. I'm going to put the results into something called PCA.save for the lack of a better name. Print comp, I put in my 3 variables. Data equals serial. Core equal true. I put that there just for emphasis. I want to make sure I get the principal component scores out. And so this is what we get. Oh, let's see here. So we can see the first principal component accounts for about 44% of the variation in the data. That's not bad, but remember, there's only 3 variables to begin with. So by default, what would one variable do? Well, essentially like 1/3. So, it's not that good. And we have 75% of the variability of the data is accounted for if you use 2 principal components. Again, think of if you just work with 2 original variables to begin with, it will be 67%. So that is an illustration of what I was showing you with that correlation matrix, that this isn't probably going to be worthwhile for us. But we could, for practice, then think about the interpretation of this first principal component. What we see here is basically what that first new variable would be, y1. It's going to be a measurement of the sugar and fat contrasted with the sodium, because the sodium has the negative value on it. The second principal component is going to be like an overall measurement of fat and sodium. I didn't include sugar because notice how that's kind of close to 0. Again, remember, we're finding linear combinations of the variables, of the original variables. If we have a coefficient on the linear combination that's close to 0, well, then that variable is not going to play much of a role. So this is a lot of good stuff here that you can look on your own that just kind of goes through the stuff that's in the output. Well, what if we use the covariance matrix? So here's the actual estimated covariance matrix in terms of the way that we would have learned how to calculate it in the data distributions and correlation section. The thing that I was alluding to before is this. The sodium variance, and this is actually on the original scale, is 6.06. The fat variance is 0.0007. The fat variance for sugar, the sugar variance is 0.02. So what is my total variance? Well, I just add up these things on the diagonal. You can see sodium plays such a huge, huge role. Let's see the effect in the analysis. Well, first of all, remember how I said that the actual estimated covariance matrix that's used by PCA, or at least the print comp function, I should say, is the bias version. This is how you would calculate the bias version, by making that little bit of adjustment. So notice here, when I use print comp, I say core equal false, so I can just use the covariance matrix. And what we can see here is that that first principal component is essentially just sodium. Why again? Just for emphasis, is because that variance is so large. Again, you're trying to explain as much variance or variability in the data as possible. So what happens in the mathematical context is this principal component essentially then says, okay, if I just take that first principal component to be essentially only sodium, I'm going to explain about 99% of the variance. So this is why this is happening. Notice the second principal component. It's essentially just sugar. Why? Take a look at the estimated covariance. Whoops. Take a look at the estimated covariance matrix again. Notice how the sugar variance is so much larger relative to the fat variance. That's why that happens. Okay. So some final questions then. Suppose more than 3 principal components are needed for a PCA. So far we've been focusing on, using some kind of scatter plot to view the principal component scores. If you needed, let's say, 4, 5, 6 principal components, how could you represent those graphically?
For 4, you could do a 3D scatter plot with the size being the 4th variable.
You could do that. So yeah, 3D bubble plot essentially. Let's actually get away from scatter plots though. What would be a way that you could represent lots of variables? What do we learn in the graphics section? Star plot would be one. What's another plot? A parallel coordinate plot. Just put the principal components as your variables. That's what you need to do. Okay? Suppose 2D scatter plots and 3D scatter plots are used to examine the PCs. But less than 50% of the total variation is accounted for by 3 PCs. Is that okay to do? What do you think? So remember, variability equates to information. So let's say 3 principal components account for less than 50% of the information that's in your data. Is it okay to still use, like, say, a 3D scatter plot to view the principal components?
If it's less than 50%, then why would we go for the 2D or 3D? Because the thumb rule we said at least about 75%.
You're losing so much information. Why would you do it? Yeah. But as long as you also say, let's say you're doing this for a research paper, as long as you just say, hey, we understand that we're missing some information, but we're still going to see if we can get some useful information out, then it's justifiable. I would always follow it up with a parallel coordinate plot, though. Okay? Notice that there are no formal inference methods in this subsection. So, we have estimated eigenvalues, but we're not doing inference at all. You might be thinking, relative to using the correlation matrix, remember we said one way to judge how many principal components to use is to see when is lambda hat greater than 0 or less than 0. I'm sorry, greater than 1 or less than 1. Well, you could do a hypothesis test for that. But no one ever does that in practice for principal component analysis. And the reason being is because this is meant to be more of an exploratory technique. Something you do at the very, very beginning of your data analysis. Later on, you're going to reach more formal conclusions by using other statistical methods. And so since this is exploratory, that's why you don't see formal inference methods used. Okay. So that's the end of that section. So today, as I said in my discussion board post, you can get together with your group in the class, work on your project. I will be here to help you as needed. If you feel as though that you don't need to get together or you're not ready to get together to discuss the project, you're welcome to leave the classroom before the 1:45 normal ending. That's okay. So it's optional if you want to stay. On Tuesday, we will start the factor analysis section. Project number 1 will be due at 5 p.m. And then looking further ahead, we will have a test on Thursday, October 23rd. Are there any questions? Yes.
While you were doing the CL example, you said that primarily you would use the correlation matrix. And in the example we saw, because when we changed the scale for the sodium, that's why the variance got high?
The reason why the variance for sodium, so when I did the second analysis, I did use milligrams for sodium, okay? and we saw the variance was 6. So that had something to do with the why it was so high. But even if I would change it over to just grams, we will still have a large differences amongst the variances. And for example, if you remember the sugar and fat, they are both measuring exactly the same scale, but there's a big difference in the variance. When you see that, then it's very, very questionable if to use a covariance matrix, because sugar will dominate fat in the analysis. Now, with the goblet data, what we found is that I didn't present this, but there wasn't as much of a difference in the variances. They were all measured on the same scale. There wasn't as much of a difference. And while the differences did play a role in the analysis, it's essentially up to the researcher or the archaeologist in this case, to make a decision of, do I want to basically unevenly weight the variables in the analysis? In practice, I probably would do it 2 different ways, with the covariance matrix or with the correlation matrix for the goblet data. Again, it is an exploratory technique. Thank you for the question. Other questions? Okay, so that's all I'm doing here today. You're welcome to say and work with your group members.